Alright, so in this video, I'm going to continue my discussion of generalized linear models, this foundational paper. And I'll include the link to this playlist and this paper in the description of this video. But in the previous video, we showed equation 1, so now we're just going to discuss equation 2. Alright, so let's see, let's go here to my whiteboard. And so equation 1 we discussed in the previous video. And so now we're going to discuss this second equation, which this says that the expected value of the second derivative of the log likelihood equals the expected value of the first derivative of the log likelihood squared. All right, and this is, driving this. It's not hard, but you do need to remember a lot of your calculus, how to take derivatives. Okay. So let's go ahead and get started and show this relationship is true. So let's get started with the left-hand side, and I'll show that it equals the right-hand side. So let's start with the expected value of the second derivative of the log likelihood function. Okay, so let's go ahead and write that log likelihood function as the log of our density, which we have theta and phi. Okay, d theta. Okay, so the second derivative. So let's start by taking the first derivative. And I'll leave that I need to take one more derivative. I'll leave that out. Okay, so I'm going to take the first derivative of the log. Now, when you take derivative of log, you get 1 over whatever you were taking the log of. So 1 over this density function. Okay. And then we would need to use the chain rule and multiply that by the derivative of the density function. Okay. Right, and we did this in this first video when we showed this first relationship for equation 1. So nothing new here, but now what's new is I need to take the derivative again. All right, so I need to find the second derivative. So you need to go back and say, okay, well, I have a product, so I'm going to need to use product rule, right? Product rule would be the first times derivative of the second plus the second times derivative of the first. All right, so let's start by, we'll write down the first piece of the product, which is 1 over our density function. All right. Times the derivative of the second, which will be the second derivative with regards to theta of the density function. Okay, and then that plus the second, so I'll go ahead and just write the second piece of the product, which is the first derivative of the density function. All right, times the derivative of the first, which will be negative 1 over our density function. All right, squared. Oops, let me write that square a little better. And then once again, I need to use the chain rule and then take the derivative of that denominator there. So that times the derivative of pi theta and phi. Okay, I'm running out of room a little bit on my board, but okay, there we go. So let's look at this carefully here. Let's pause here for a second. I'm seeing this piece show up twice, right? And it's a product, so I could just write that as it being squared. So let me go ahead and rewrite this again. I'll leave the first half, I'll leave this alone. So I have 1 over the density function times phi, the second derivative of the density function, okay, I'll pull that negative sign out front, so I have minus instead of plus. And then I have 1 over the density function squared, or actually since both these are squared, I'll use large parentheses to square both. Okay, so both these are squared. All right. So now, let's look at this. Let's think about this for a minute before I keep moving forward. Well, actually, one more thing I can do is go ahead and separate this expected value into two separate expected values, because the expected value of a sum is the same thing as the sum of expected values. So that's using a property of expected value. So let me go ahead and do that really quick. Okay, so the second derivative of the density function with regards to theta. Okay, so that's one expected value, and then minus the expected value of this jazz. Oops, that should be theta and then phi. All right. So all this is squared, and then I'm taking the expected value of it. Okay, so this is, I'm going to pause here and think about this. This is kind of the main trick for showing this relationship in equation 2. We need to pause here and then look at this inside the square, all right? And notice that this is the same thing as the first derivative of the log of the density function. Okay. This inside of here. Why is that? Well, you can prove this yourself, right? So if I were to take the first derivative of the log, right, I would do 1 over what's inside the log times the derivative of what was inside the log, right? So this is the same. What I've highlighted here in blue and what I've written here in blue is the same. All right, and that's kind of a key part to showing this relationship in equation 2, right? So I still have the expected value of this this section here in blue, and then it's still squared. All right. All right, so now this first part of the equation, I kind of just dropped that for a second. We're going to go ahead and need to find this expected value. So to find an expected value, we'll do the derivative of 1 over pi, the density function, second derivative of the density function, times the density function, right? That's how you find expected value, is you write what you're trying to find the expected value of, and then you multiply it by the density function. And then you integrate that over z, your random variable z. Okay, so for this part of the equation here, we notice that this part here will cancel with this part here. All right, so you end up with the derivative of the second derivative dz. And then this piece here, this is the same thing as the expected value of the first derivative, and this is basically the log likelihood function. Okay. All right, so now I can reverse this integration and interval using is it Lebanese integral rule, which, as long as we assume that the bounds of z don't depend on the bounds of theta, then we're good to go, and we can reverse the integration and the derivative like this. Okay, and I can do my integral first and my derivative second. Okay, I'm just going to keep writing this, so copy this down. All right, so the integral of a density function, by definition of what a density function is always going to be 1. Okay, and you can see we're almost there, because now the derivative of 1 is 0, and then if you take the derivative again, you get 0. So the second derivative is 0. And then here we go. We're at the end where I've shown that the expected value of the second derivative of the log likelihood function with regards to theta equals the negative expected value of the log likelihood squared, right? And that is what equation 2 says.